Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss linear monoatomic vibrations. Let's begin. To show linear monoatomic vibrations, we have to assume some points. First point, atoms are arranged linearly in a straight line, and the interatomic spacing is a constant. That interatomic spacing, the distance between two conjugative atoms, is a. And small m is the mass of each atom in that of crystal is same. As the name indicate, monoatomic, throughout that of crystal there will be a single atom. The atom is supposed to be a rigid sphere in that of crystal. The crystal is under the influence of short range forces, where the interactions between the atoms are confined to only the nearest neighbor, or we can say only due to its conjugative atoms. Each atom in one dimensional monoatomic lattice is connected with a spring, and here we consider that spring having the spring constant alpha, and that one is massless. The force on the atom is directly proportional to the extension or contraction of its nearest neighboring distance. All the atoms in linear array and they obey Hooke's law. For simplicity, we consider only the longitudinal mode of vibrations. A linear chain of identical atoms extend along the x axis. In xy plane, we consider the linear atoms. Are arranged monoatomic. Throughout that entire crystal there will be same atom. If we prefer that one is the nth atom, then its neighbor atoms as n minus 1th atom and n minus 2th atom. Again it will be n plus 1th atom, it will be n plus 2th atom, and so on, n plus 3th atom. These atoms are interconnected with each other with a spring having the spring constant alpha. And the distance between two atoms, two nearest atom, is small a. For nth atom, that distance will be n plus a, sorry, n a distance of that of nth atom. from the origin. At nth position we have that nth atom. At the mean position, the distance of nth atom from that of origin is Na. When the crystal lattice starts vibrating, the atoms gets displaced by a small magnitude. Let we choose from that of origin n minus 2th atom is at a distance of x n minus 2, that atom is at a distance of x n minus 1, nth atom as at a distance of x n n plus 1, n plus 1 x n plus 2, that atom at a distance of x n plus 3. That is the displacement of these atoms. From their respective mean position. That atom is displaced to its respective mean position, this atom respective mean position, nth atom displaced to its respective mean position. That atom therefore, the spring joining nth atoms and n plus 1th atom extends by x n plus 1 minus x n, and it executed a force. That force is the spring constant into the displacement of nth atom. Therefore, we write as is shown in that of figure, at mean position the distance of nth atom from the origin is Na, and when the crystal lattice starts vibrating, the atoms gets displaced by a small magnitude. Let that small magnitude x n minus 2, x n minus 1, x n plus 1, x n plus 2, etc. be the displacement of x n minus 2 is the displacement of n minus 2th atom, and x n minus 1 is the x minus n minus 1th atom, nth atom, n plus 1th atom, n plus sawtooth atom, etc. atoms respectively from their mean position. Okay, these are the displacement of these atoms from their mean position. So, what amount of force executed? Hence, the force on nth atom is due to the spring joining nth and n plus 1th atom that extends by x n plus 1 minus x n, x n plus 1 minus x n. And exerts a force, that force is the spring constant alpha into that of displacement. Displacement is x n plus 1 minus x n. On nth atom. And exerts the force alpha into x n minus x n minus 1 on nth atom in opposite direction. So, one force is applied, that is alpha into x n plus 1 minus x n on that of nth atom. Another force also applied on that of particular nth atom in opposite direction. Therefore, the net force F is equal to alpha, that force x n plus 1 minus x n minus alpha, this force x n minus x n minus 1, or the force F when we apply the Newton's second law of motion on that of nth atom, the force is mass into acceleration. So, mass of that of atom m, acceleration, that is the second order differentiation of the displacement, second order differentiation d square xn divided by dt square is equal to, taking alpha as common, you have x n plus 1 minus xn plus x n minus 1, or m d2 xn dt square is equal to alpha x n plus 1 plus x n minus 1 minus 2 xn. This is a kind of differential equation. So, the solution of that kind of differential equation, is equal to xn is equal to a e to the power I k n a minus omega t. That be the solution of this differential equation. From that solution, the points where a, that is the resultant amplitude, of the wave, omega, angular frequency, of the travelling wave, k, the propagation constant, and which one is equal to 2 pi by lambda, whereas lambda be the wavelength of resultant wave. Here we see, although the amplitude A is same, but the different atoms in the crystal vibrate in different phase, which increases from one atom to the next atom by the factor k into A. Now, we differentiate that equation twice with respect to time. Differentiating equation number 2 twice with respect to time, we get, that is d square xn divided by dt square is equal to I square omega square a e to the power I k n a minus omega t. Or d 2 xn dt square is equal to I square minus 1 minus a omega square e to the power I k n a minus omega t. And also xn is equal to that much. Therefore x n minus 1 is equal to a e to the power I k n minus 1 a minus omega t, and x n plus 1, that will be the displacement of n plus 1th atom. A, for n plus 1, in place of a we substitute n plus 1, e to the power I k n plus 1 a minus omega t. Now we substitute all these values in equation number 1. Therefore equation 1 becomes m d square xn by dt square m d square xn by dt square, the value is equal to that much. So minus a omega square e to the power I k n a minus omega t is equal to alpha whole into x n plus 1 x n minus 1 minus 2xn x n minus 1 x n plus 1 x n. In all these terms there will be a common term. First we put these values. First one alpha a e to the power I k n plus 1 a minus omega t plus alpha a e to the power I k n minus 1 a minus omega t minus 2 alpha a e to the power I k n a minus omega t. Now from these two sides e to the power I k n a minus omega t cancelled out and a also cancelled out on both sides. We have minus m omega square is equal to alpha taking as common e to the power here I k a plus e to the power minus I k a minus 2 is equal to alpha e to the power I k a e to the power I theta is equal to sin theta plus I cos theta, exponential function in terms of sin and cos. E to the power I k a is equal to cos k a plus I sin k a. Again e to the power minus I k a is equal to cos k a minus I sin k a minus 2 plus I sin k a minus I sin ka cancelled out, alpha 2 cos ka minus 2 cos ka minus 2. Now 2 was common, we have 2 alpha cos ka minus 1 is equal to 2 alpha. In place of cos ka we write 1 minus 2 sin square ka by 2 minus 1 as cos ka in terms of sin 2a. So plus 1 minus 1 cancelled out, we have minus 4 alpha sin square ka by 2. On these two sides the negative cancel out, and omega square, let me write m omega square is equal to 4 alpha sin square ka by 2, or omega square is equal to 4 alpha by m sin square ka by 2, or omega is equal to its under root as 2 alpha by m under root sin ka by 2. Omega is equal to that much. Or omega is equal to 2 under root of alpha by m, as we prefer as omega naught sin ka by 2. Here we prefer omega naught is equal to 2 alpha by m under root, that one is maximum angular frequency. Maximum angular frequency, and that equation omega is equal to omega naught sin ka by 2, this is known as the dispersion relation. Dispersion relation because it relates omega to k, to propagation constant. Therefore that relation is known as the dispersion relation, and from that of dispersion relation we can also achieve the frequency, or omega naught is equal to 2 pi f is equal to 2 alpha by m under root. Therefore f is equal to omega is equal to 2 pi f. To cancel out, So f is equal to 1 by pi alpha by m under root, that is the frequency, and that frequency is known as Einstein's frequency. Einstein's frequency. An important relation we achieve as omega is equal to omega naught sin ka by 2, which one is known as the dispersion relation, the relation in between omega, angular frequency, and propagation constant k. When we plot a graph between angular frequency and propagation constant, plotting a graph between angular frequency and propagation constant, and look here, since we have the value of omega as it is the square root, we have two roots, but we consider only the positive roots due to obtaining the real frequencies. See, the maximum angular frequency, in that of axis we have omega, and in that of axis we have the propagation vector k, x o x dash y. The graphs we have obtained. Like this. Here pi by a, 2 pi by a, 3 pi by a, pi by a, 2 pi by a, there 3 pi by a, that is the negative side. And when we take that relation for small values of Ka, for small values of Ka, then for small values sin theta is nearly equal to theta, therefore omega is equal to omega naught sin Ka by 2, that is nearly equal to in place of omega naught we substitute the value as 2 alpha by m under root sin Ka by 2 as Ka by 2, or omega is equal to 2 to cancel out, alpha by m to the power half into Ka, therefore omega by k is equal to alpha by m half into a omega by k, that is nothing but the phase velocity, alpha by m half into a, that is the phase velocity. Again if we differentiate that quantity d omega with respect to dk, so we obtain d omega with respect to decay. So, d of decay in place of omega we substitute alpha by m to the power half Ka, or d omega by decay is nothing but group velocity. So, its differentiation, that one is a constant term, alpha by m half differentiation of K A. That is the group velocity. From these expressions, for phase velocity is equal to group velocity. Here, for small value of Ka, phase velocity Vp is equal to group velocity V of G. And for the value of K is equal to pi by A, group velocity becomes 0. In general, we can say, Vg group velocity is equal to 0 when the K is equal to pi by A plus P, where P is any integer. That indicates the K periodic dispersion is consequence of translational symmetry in that of crystal, that is omega naught, maximum angular frequency. Now, the Brillouin zones we obtain if the value of K in between pi by A to minus pi by A, then we obtain first Brillouin zone. This is pi by A to minus pi by A. Here we obtain first Brillouin zone. This be the graph. In that of region we obtain first Brillouin zone. Next, for second Brillouin zone, K from minus pi by A to minus 2 pi by A and K from 2 pi by A to 2 pi by A. Here we obtain second Brillouin zone. Minus pi by A to 2 pi by A in that of section plus pi by a to 2 pi by a in that of section, where we obtain second brilliant zone. Second brilliant zone, that is for second brilliant zone. Next, for third brilliant zone, it has also the two regions. Here K in between minus 3 pi by a to minus 2 pi by a, and K in positive section as 2 pi by a to 3 pi by a, that we obtain third brilliant zone. Third brilliant zone. See that a figure. In that region, we obtain third brilliant zone. 2 pi by a, 3 pi by a. Here we obtain third brilliant zone. Okay. Here, with the help of this video lecture, we understand the concept of linear atomic vibrations. We assumed some point to show the linear atomic vibrations. Consider the linear arrangement of atoms. The net force on nth atom due to these two, and solving the solution of the differential equation, then putting the values of these corresponding terms, and finally we have omega is equal to omega naught sin k a by 2, that is the dispersion relation between omega and k. By using that omega and k, we plot the graph. From that of graph, we can easily show for phase velocity and group velocity is same for the small value of Ka, and that indicates the generalization of the value of K. By generalizing that value, we can obtain the brilliant zones as first brilliant zone, second brilliant zone, and third brilliant zone. So, with this useful and informative notes, let me wind up this session. Thank you.